All right, let's start with the next circuit, which is the three-phase circuit and which is a six-pulse circuit, right? So if you see, it is a six-pulse circuit. It's also a three-phase circuit, right? Earlier we saw a three-phase three-pulse circuit, which had a problem in terms of the input DC current. So this circuit is very similar to a full bridge circuit, right? In full bridge circuit we saw that it was a single phase, so there were four diodes. Here instead of four diodes we have six diodes, and we have a load. Let's call this current I, let's call this voltage VO, right? And each of this is connected to one of the voltage sources. Voltage source VAN, VBN, and VCN. Right, and there are six diodes. You would see different literature naming them differently. Let me for simplicity call the diode connected to A phase as DA1 and DA2, similarly DB1 and DB2, and DC1 and DC2, right? This is your complete six pulse rectifier circuit. Let's try to draw the waveforms for the circuit. Again, let us assume phase sequence ABC. That means phase A is leading, right? Followed by phase B, followed by phase C. And this is where you complete the 360 degrees, right? This is 30, 60, 90, 120, 150, 180, right? This is the half cycle, and then the remaining part is the complete cycle. Now the question is, which devices would conduct in which part? Let's also again consider that load has large L, right? Or it could be also written as load current is continuous, right? It's operating in CCM, and in that case, out of the top three diodes, at least one diode has to conduct, and similarly out of the bottom three diodes, one diode must necessarily conduct. So let's start first from the top three diodes. Again, the one which has the highest anode potential will conduct. So you can see that between 0 to 30 degrees, it will be DC1, right? And between 30 degrees to remaining part, 30 to 60, 60 to 90, 90 to 120, it will again be C1, C1 and C1 diode DC1s, which would be, sorry, not C1, it will be A1, A1 and A1, because VAN has the highest potential, and again it will be A1, right? So all of these would be A1s, and then again at this stage it would be B1, right? So this is roughly the top diodes. Similarly, we can see for the bottom diodes, DA2, DB2, DC2, and see whichever has the negative most potential will conduct. So here it will be B2, right? Then it will be, sorry, I'm using small, so it will be B2, then it will be again B2, then it will be again B2, and then it's going to be C2, then C2, and then C2, right? So we have decided which devices would be conducting in this period. Let me just rewrite this A, which does not really look like A. Let me rewrite them and make sure that they look like A, right? Yeah. So once we decide on which diodes are conducting, then you can actually see the voltage. So what is voltage? V1 or VO? VO is nothing but the voltage of the positive terminal with respect to the neutral minus voltage of the negative terminal with respect to the neutral, if this is neutral, right? So it's the difference of the positive and the negative voltage. So you see that if you want to now draw what is VO, right? Let me try to extend these. So between 0 to 30 degrees, it's going to be the difference between, since C1 is conducting from the top, so the top part is nothing but VCN, and since B2 conducting the bottom, this is nothing but VBN. So VO is VCN minus VBN. So VCN minus VBN. Right. So so this is the voltage which is going to appear is nothing but VN minus VBN in this case. So you can probably indicatively draw it. Right, and then it will be VA minus VA1 minus VBN, so it will be VAB, then again it will be VAB, right, then it will be VAC, and then again it will be VAC, and then it will be VBC, right, and so on. So this is how roughly the output voltage would look like. So if you see here, you have 1, 2, 3 pulses in half cycle, so you'll have another 3 pulses if you completely draw it, so you'll have total of 6 pulses. So you can understand, going from 3 pulse to 6 pulse, your ripple would further reduce and therefore your quality of output current would further improve, right? So that way this circuit not just only takes care of the input DC current but also ensures that the output voltage current ripple and the voltage ripples are small. Now regarding the current, you can see yourself and you can understand that, for example, the DA will conduct in this duration, right, DA1, and DA2 will conduct in this duration, and therefore how would the current look like? If you want to draw the current, which is IA, which is the current supplied by the source A, it is nothing but going to be 0 plus from 30 degrees to 150 degrees, and then again 0, and then minus, and then again 0. So you can see it's a nice symmetric waveform. It's a half wave symmetric waveform which has an average value of 0, right, and therefore the problem which was existing with 3-pulse circuit is no longer there. Okay, so far we have talked about diode rectifiers. Now we would talk about some of the other rectifier circuits in subsequent videos. Before we move ahead, let us quickly see what is the motivation. Why do we want to move to other circuits? Obviously, one of the motivation is what we discussed previously, and you can see still that your current IA is not a sinusoid, right? It has harmonics, it has lower order harmonics, and you would like to avoid those. That part we would probably do sometime later, but another immediate motivation that you can see here is that your output voltage, if you see the output voltage waveform, that is a function of input voltage, right? So if your input voltage changes, your output voltage also changes. But you do not have any control over output voltage other than the input voltage. So let's say it may happen that your input voltage suddenly fluctuates because of grid voltage fluctuation, right? Then your output voltage will also fluctuate. Let's say you are using this output, your load is actually, let's say, a DC motor, right? So if your load is a DC motor, let's say you want to change the armature current, you want to change the armature voltage, right? If you want to change the armature voltage, you want to change VO, but in this case you cannot change VO because it depends on the input voltage. At best, what you can do is you can connect a variable resistor, right, variac, at the input side, right, where you have VAN and you have VAN prime, and this VAN prime you can give to the rectifier circuits. Then you can, by controlling the tappings here, by controlling which tap do you connect to on this side, or rather on the high voltage side usually you have tapping. So depending on which tap do you connect to, you can manipulate VAN prime, and therefore you can manipulate the rectified output voltage VO. But using a variac, as you would have seen in labs, usually variacs are heavy equipment, right? They are not very lightweighted. You can imagine a diode and compare it with variac. Diodes are usually small, they are semiconductor devices. On the other hand, variacs are heavy, they are big, and so on, right? They are made up of windings, they are made up of core, so they are expensive also in general. So therefore there is a need to look for some other solution wherein for a fixed value of input voltage you can manipulate the output voltage without using a variac, right? So that is precisely what we are going to do in our next video.